Hello RMS Algebra. Welcome back for another review video. Today this one will be going over sequences and how we can write recursive and explicit rules for both arithmetic and geometric sequences. So let's start right away by taking a look at an arithmetic sequence. Remember that those were sequences that grow by addition. They might also look like you're subtracting, but that's really just adding a negative. So let's just pick a sequence like 7, 12, 17, 22, and it'll continue in that same way. So that's our sequence. Again, that's arithmetic because we're adding 5 each time as it grows. So if I want to write this recursively, that recursive rule means that it's going to build from itself. So I can do t of n represents a term, and that'll be equal to the term right before it, which would be t of n minus 1, because minus 1 takes us 1 before that t of n term. So the term before is t of n minus 1, and then I know I need to add 5 to that, and that'll get me to the next term. We also need to be sure we include one of the values of a term in this sequence, like the 0th term, so that we can build this sequence just by seeing the rule. So the 0th term would be 5 before 7, or 2. In class, we've also written these other ways. Another way to write a recursive rule would be to start with t of n plus 1 instead of starting with t of n. But now because I've done n plus 1, the term right before that would just be t of n. We'd still be adding 5. That t of 0 equals 2 would still work. The only thing we changed was the t of n plus 1 and t of n. But those are both recursive rules for that arithmetic sequence. To write the explicit rule, well, we've got a couple options here as well. So for explicit rules, we started out, we wrote them in the 0th term form, and that looked something like t of n is equal to whatever our common difference was. Here it's 5 between each term, times n, which represents our term number, and then we'll add or subtract the 0th term, which is 2. We can check that. If we want to calculate the third term in the sequence, we'll say, okay, t of 3 is equal to 5 multiplied by 3 plus 2. So t of 3 is equal to 15 plus 2, or 17. And fortunately that matches our sequence, so that equation works. To write this sequence in first term form, instead of using the 0th term in our equation, somehow we have to incorporate the first term. So t of n will be equal to, well, we're still growing by 5, but this time, instead of 5 times n, it's going to have to be 5 times n minus 1, because we're bumping everything one term forward by adding 7 instead of 2. So because we've changed that, we have to make sure it's n minus 1 and not just n. And the same thing to check that, we could do t of 3 is equal to 5 multiplied by 3 minus 1 plus 7. And so that says the third term is equal to 5 times 2, which is 10, plus 7 equals 17. So those are both acceptable ways to write the equation for an arithmetic sequence. So I know I went quickly there, but you've got this video. You can pause it, rewind, and go over what I just said before you move on and look at the same ideas for a geometric sequence. So let's go forward to a geometric sequence. For this one, let's look at the sequence generated as 4, 16, then 64, and it'll continue growing that way. So this is geometric, And we can tell that because we're multiplying by 4 each time. So since it's a geometric sequence, let's talk about how we write those recursive and explicit rules. The recursive rule is similar to that for the arithmetic sequence, where we'll still be looking at a term like t of n, and to get to that term, we'll take the term right before it, which is t of n minus 1, and then, well, it looks like we have to multiply by 4 every time. So that's our recursive equation. We also need to know that that 0th term here would be equal to 1, and then we could generate that whole equation. We could also do it by writing t of n plus 1 and saying that was equal to t of n, which is right before it now, times 4. We'd still need that t of 0 equals 1 piece of information though. But both those are acceptable recursive equations. For the explicit rule, well, it's the same thing as before. We could have a 0th term equation or a first term equation. So for the 0th term, well, we'll write t of n is equal to, well, we're growing by multiplying by 4 each time. So we'll have 4, and to repeatedly multiply, we'll put an exponent on that of n. We also need to incorporate our 0th term, which in this case is just 1. So t of n is equal to 1 times 4 to the nth power. And if we check that, let's look at the second term this time. So t of 2 is equal to 1 times 4 squared. Well, that means that t of 2 is equal to 16, which matches our equation. If we write this same thing in first term form, we'll still use t of n. This time, instead of using that 1 or the 0th term as our starting value, we'll use 4 as the starting value. We're still growing by multiplying by 4 each time. However, to keep from being 1 ahead the entire time, we need to do n minus 1. And if we check that with t of 2, we get this equation, which says that the value of the second term is equal to 4 times 4 to the first power, which is just 4 times 4, or 16. So, matches again. Both those equations work, and now we have ways to write recursive and explicit rules for both arithmetic and geometric sequences. Your homework today is just a brief assignment practicing this on a few equations, or sequences I should say. Please take a look at that. You can do it on your own paper and just take a picture of it and submit it on Google Classroom when you're done. If you have questions along the way, please see me during office hours from 9 to 11 and just post a quick comment and I'll get back to you right away with how you can solve those problems. All right, guys, good luck.